Hello, I am Hans Golf 0 Uniform Papa Lima, and this is my update on the Qcx Mini transceiver kit. For those of you who are not aware of the Qcx was a 5-watt single-band CW transceiver introduced in August 2017, packing very high performance and many features, but at the low cost of $49 for the kit. It's shown here in the Tech, which is a third-party aluminium enclosure. It has a 5 watts output and many features such as VFO-A, VFO-B, split operation and memories, presets, and a big feature is all the built-in alignment tools. Over the following 3 years, almost 10,000 of these kits were sold, which is a tremendous success story. In May 2020, the Qcx was replaced by the Qcx Plus, which was a larger board, more than twice the board area, and a very nice extruded black anodized aluminium enclosure. You can see here the board area much bigger, the components spread out much more, so it's somewhat easier to build and it's really very good for modifications. Also sporting here a TCXO module option as well, and more connectors on the back, including a PTT output for the 50 watts power amplifier kit and a serial port for CAT control. Qcx Plus was extremely popular, but there were people who preferred the original form factor of the Qcx, which was very suitable for portable operations. Accordingly, in December 2020, we introduced the Qcx Mini, which is a miniaturized version of the Qcx Plus. It has all the same ports as the Qcx Plus, the same features, the same schematic, the same firmware, operation, performance, everything the same as the Qcx Plus, except in a really tiny form factor, and again very suitable for portable operations. It has about half the current consumption due to the yellow-green LCD, which can be switched off for outdoor operations and full sunlight visible, and it also is much lighter than the Qcx Plus or indeed the original Qcx. Qcx Mini is really insanely cute and has been selling at a much faster rate even than the original Qcx or the Qcx Plus, but there were some issues with the first batch of kits. Really, there are 3 categories of issues affecting the first batch of kits. The first one was the voltage regulator chosen, which turned out to be a rather fragile choice of voltage regulator. The second one was production issues with the surface mount soldering factory, and the third issue was that several of the op amps could be defective, and we heard several reports of this, which was really not expected. So all 3 of these issues, needless to say, did not show up in the research and development or the testing, and so were quite a nasty surprise. It is the first really QRP Labs kit with a significant amount of surface mount devices already pre-soldered onto the circuit board, and so there are undoubtedly some lessons to be had in this. So the rest of this video is about how these 3 problems have been resolved in batch 2, and going forward you can have very good confidence that the supplied boards will function properly. So here is a Qcx Mini Rev 1 board. You can see the Rev 1 indicated here. And if I just take this apart, the voltage regulator is this 3-terminal device down here near the power input, and is the AMS 1117 5-volt fixed voltage regulator. Now there are 2 different manufacturers which both make an AMS 1117, and there are a large number of other manufacturers which also produce 1117 variants with different prefixes. So it doesn't help from the start that there are 2 manufacturers and you're not sure exactly which chip you've got, and there are 2 different datasheets with different specifications from all the others. It turned out that the capacitor C38 on the bottom of the board here, which is at the input, is a multi-layer ceramic capacitor, and these have the feature that the supply voltage affects the capacitance, and at about 12 volt supply that capacitance of nominally 10 microfarads has already dropped to about 2 microfarads. And it turned out that this caused instability in the voltage regulator during power on or power off glitches, and these glitches could actually destroy the voltage regulator. A problem with that then was that the voltage regulator fails in a short circuit mode, so it connects its input to its output directly, and that puts 12 volts onto the 5 volt rail, which feeds the FST3253 multiplexer chip here, and the SI53518 synthesizer chip here, as well as the microprocessor here, and on the bottom side the 74ACT00 transmitter driver. All of these 5-volt components are likely to have been destroyed very soon after that voltage regulator fails, and so the failure mode is really nasty of this voltage regulator. Somewhat solved by putting this additional 10 microfarad capacitor in parallel with the input, which should be a tantalum or an electrolytic capacitor, and that was shown to solve that problem. But still, the voltage regulator is quite delicate, and people found, for example, that if plugging in something to the GPS port here or the PTT port, if hot plugging, you could short the 5-volt rail to ground, even temporarily, or any kind of short whatsoever is enough to destroy that voltage regulator, and with it all the 5-volt systems downstream. So it's obviously a very fragile voltage regulator. It does work. It's not that it fails completely, it's just that it's quite easily damaged. So that was a bit of a disappointment that hadn't shown up in testing. This is a batch 2 board, revision 2 board, and you may be able to see revision 2 written there at the top right corner. And here we've replaced the voltage regulator with the LM78M05, which is a slightly lower current version of the original 1 amp 5-volt regulator in the original Qcx and the Qcx Plus. These are a very, very well known and very common and robust voltage regulator. I can't remember ever having seen one fail. They certainly put up with short duration, short circuits and all kinds of other abuses. So that replaces the voltage regulator with a much more robust voltage regulator. The additional capacitor is no longer required. The second problem was in the SMD factory. It turned out that some of the boards had been subjected to manual rework. Of the 1,000 original boards, 33 of them had failed the SMD factory's control and had then gone on to manual rework, which had, humans had sat there fixing any issues with the boards. And in many cases, the soldering was very poor, and in some cases there were cracked components, intermittent joints, and so on out of those 33. So that was very disappointing, and it turned out that a subcontractor of a subcontractor had been changed because the original subcontractor had been out of business during the coronavirus pandemic, and of course I hadn't been informed of that, and so the newer factory was obviously not such a good quality as the one we had previously been using. So to resolve that, we've actually changed the SMD assembly house to a different one after some research to find a good quality SMD facility. The third problem that we had was quite a few people reported defective operational amplifiers. So that's one of these 5 operational amplifiers. This is IC10 here, the audio output amplifier, and then there's IC8 and 9, these two here, which are the CW filter, and IC6 and 7 here, which are the audio phase shift circuits. And all of these operational amplifiers are type OPA2277. And it appears that somewhere in the supply chain there have been some defective op-amps introduced. Either that, or during the assembly there were defective op-amps caused perhaps by too much heating or I don't know what. And some of these op-amps were actually defective in the supplied boards. Now, many people were very good about this and changed their op-amps, and of course it only affected a small percentage of people anyway, but a much higher percentage than I would be comfortable with. And so what we've done for the second batch is develop a very comprehensive test suite. This is the test jig that was developed, and all 1,000 assembled boards of the second batch have been through this test jig to verify the correct operation of the board. So I'll tell you some more about this because it's quite an interesting project in its own right, and was quite a bit of fun to design and produce, and of course it's been extremely useful. The most important component which makes this possible is called the Pogo Pin. These are Pogo Pins, and they have the interesting characteristic that inside there's some kind of spring, and you can see that the contact here is compressible. It depresses about 2 millimeters or so under pressure, and these come in all kinds of shapes and sizes. The ones I chose here were supposed to have a base here which would fit into the holes for the through-hole components in the Qcx Mini board. In the event, it turned out that the dimensions of the Pogo Pins were not the same as the datasheet had claimed. The diameter is slightly more, so I had to drill out the holes slightly, but nevertheless they've worked quite well. Now if I open up the device here, you'll see that inside there is a Qcx Mini board, and I've removed all of the SMD components from both sides of the board with a very low-cost hobby hot air gun, and I've actually inserted here 54 different Pogo Pins at various strategic points across the circuit board where through-hole components would normally be inserted. So on the bottom side of this board, I've reproduced all of the through-hole components that would normally be in a Qcx Mini, but none of the SMD components. All the SMD components have been removed from the board with the hot air gun. And so what you get when you plug in the board under test with its SMD components on it, but none of its through-hole components, is a mating of this through-hole assembly with all the through-hole components on the bottom side of the board with the board under test with the SMD components on it, and you actually reproduce a complete functional Qcx Mini kit. So on the bottom side of the board you'll see the power amplifier transistors here, the output low pass filters, all of the through-hole capacitors, and the crystal here for the 27 MHz oscillator, reference for the SI53518A. You do not see the trimmer capacitors. What I've done is replace those with fixed resistance ratios, as well as the gain control, which is also external control on the front panel of the testing jig. I've also added here a 47 ohm junk box resistor, quite an old one really, which is used as a dummy load so I can test the transmitter. There's quite a lot of pressure required. The individual pressure to depress one of these Pogo Pins is not really noticeable, but it is, I've tested, it's around 100 grams of pressure to compress it by about 2 millimeters, and so when you have 54 of them, you're talking about 5 kilograms of force required to sandwich the two boards together. So in order to spread that load evenly across the board under test without warping it and potentially cracking joints, I got this piece of MDF which I cut to the correct size of a Qcx Mini board and milled out with a drill areas where the top of the circuit board has ICs on it so that they don't get put under pressure, and all of these areas that you see that are unmilled actually make contact with the top side of the board under test and apply a fairly even pressure across it so that you don't end up warping that board at all. There are then 5 M3 bolts that come up through the board, and they fit through the mounting holes in the Qcx Mini board under test so that they ensure a precise alignment. So you can see as I put the test board on, it slides nicely over those alignment bolts and fits very well indeed. There are then these hinged flaps at the side, and each of those is a piece of unetched PCB material which is soldered onto a brass tube and a screw on either side to hold them in position, and so those hinge quite nicely. And what happens is you put on the load spreading block on the top, push it in, push down with about 5 kilograms of force, and then squeeze the sides together, and that holds the board in place very well. On the front panel here of the unit, we have from left to right, we have a 128 by 64 pixel OLED display with a 0.9 inch diameter. The reason why I chose this was because it has a I2C bus, so just 4 pin connections, the power and the I2C bus, and I can share the I2C bus with the SI53518A chip, and that gives me 6 additional pins of the Amiga 328 processor in which to connect to the board under test and make measurements. Then there's one side here of and a pair of earphones, and that's just glued into a hole on the front panel. There's a red LED and a green LED which indicate fail or pass of the tests, and this is the gain control, which is just soldered in place of the original gain control on the Qcx Mini, and finally an on-off switch here on the right hand side. If I look at the back here, and yes, this does require really a rear panel and a bottom panel, I just haven't got around to that yet. You can see in here the usual Amiga 328 processor. There's a 5V 7805 voltage regulator. Here's a 2.1mm power connector, and there are two relays. You may recognize these from the QRP Labs relay switched low pass filter kit. And these are used to expand the number of analog inputs from 4 to 6. And one of those is used to switch in an additional resistance in parallel with the high or low phase trimmer potentiometer, so that it can make an adjustment there and see if the null is deepened during the phase adjustment procedure. This Amiga 328 runs a special version of the firmware for the Qcx. It's not really a Qcx firmware at all in the end, but it was derived originally from it. And it runs 21 different tests on the board under test. There's also here a serial output, and so I can actually log the test results as they happen to a PC via a serial to USB converter. Completion of a successful test result, we've stuck this QC pass sticker onto the outside of the static proof bag, and also made a note on the outside bag of a batch ID number, in this case 577. That lets me cross-reference into a database of all the test results which I'm keeping on the PC, so that in future, if any problems arise, we'll be able to look back and see exactly what the test results were and find out whether or not the test result constraints need to be modified in any way. That's the pass-fail criteria. This was the original diagram that I was working on to indicate the position of all the Pogo Pins I had used or originally planned to use. Of course, there was some later changes, and the schematic later became the victim of a water spillage which has blurred some of the ink, and so these normal type of lab dramas that go on. Now there are 5 points in the receiver chain, which is the I output of IC5 and the Q output of IC5. There's the audio 2 position here, which is one of the existing sample points in the Qcx Mini. And then there's the output of the CW filter, which is also being sampled in my test jig, and finally the output of the overall receiver. And so by checking the DC bias levels at each of these 5 points, and also the amplitude of the signal under various conditions in the alignment procedure, such as the bandpass filter peaking and the IQ balance and the unwanted phaseband cancellations, by looking at that I'm able to find out what is the unwanted sideband cancellation, which indicates whether there is correct phase shift in the two phase shifting circuits here, which are IC7 and IC6. I'm able to find out whether the gain of the CW filter is correct. We're expecting about 18 or 19 dB of gain through the CW filter. I also inject a signal which is at 500 Hz and one at 900 Hz, so they're somewhat further off the center frequency of 700 Hz, and you can check that they're attenuated as you would expect by the CW filter. Furthermore, I check the gain of this final audio amplifier stage here, which tells me that the final audio amp is working properly. On the oscillator, I'm checking the output of the SI5351A oscillator here to make sure that that's oscillating properly and there's correct I2C communication on the I2C bus between the microprocessor and the SI5351A. I'm checking the transmitter power output at the RF output here and making sure that I get somewhere around 4.5 watts with a 12 volt supply. Of course, that wasn't particularly easy to see on hand-drawn modified schematic, but here's a block diagram which may be easier to follow On the top row you can see the receiver signal path and the 5 connection points to that at the I and Q output channels of the preamplifier, the audio 2 output, which is actually the combined I and Q path after the phase shift. CW is the output of the CW filter, and then finally the audio output at the top right of the diagram. The SI5351A CLK2 output is tested and measured via the frequency counter input of the microcontroller, and the RF output in transmit mode is measured with a diode detector. The microcontroller also supplies the necessary control signals to the Qcx Mini circuit, including the transmit-receive switch, the I2C bus to control the SI5351A, muting signals, keying signals, and so on. Here's a sketch of the controller for the test jig. The microcontroller controls 2 relays which switch between the analog channels up here to give me 4 channels on 2 inputs, and also connects the extra resistor in parallel with the lows phase trimmer adjustment potentiometer, which is a fixed divider on the bottom of the board, and a 7805 voltage regulator here at the bottom. It did change slightly from when I drew the diagram, but nothing major. So here's a list of the 21 tests which are being performed by the unit, and each one of these, the result is checked to make sure it's between certain bounds, and if there's a fail in any of those 21 tests, then the entire board is branded a fail. The first test just looks to see whether there's 5 volts, and that tests the voltage regulator. The second test checks the SI5351A to make sure there's communication, and also to make sure the output frequency is correct. Then I check the transmitter output power, and it should be around 4.5 watts. I check at the audio 2 output in the receiver bandpass filter calibration mode to make sure I have a nice strong signal of the right level. The receiver I and Q signals should also be the same level as the original bandpass filter level. There's not supposed to be any differential in that area. Then IQ balance, and this is measured right here at the final output stage of the receiver. You should notice the volume getting quieter. When it's in the IQ balance mode, it's checking for minimization of the unwanted sideband. We also check the AF gain. This is the gain through the final audio amplifier, and of course that's dependent on the gain control setting on the front of the test jig, but anyway, if it's within a reasonable range, it's considered to be a success, and we generally find that works very well. There's the gain of the CW filter here is measured quite accurately. It should be around 18 dB. We sometimes see 18, 19, 20, that kind of level. And then, as I said, a 500 Hz and a 900 Hz tone injected, which makes sure that the skirts of the CW filter are significantly attenuated, which proves that the CW filter is working, which again indicates then that IC8 and IC9 are operating correctly. We then inject the unwanted side tone in the high phase adjustment and the low phase adjustment, and make sure that the audio amplitude is significantly less when we go into those settings. Furthermore, then we switch on a relay which applies an additional resistance in parallel with the low phase trimmer, and that always produces an improved unwanted sideband cancellation. We then turn on the side tone and make sure that we get a loud side tone output, and switch on the muting transistor to make sure that that significantly attenuates the side tone output. And then finally I'm measuring the bias at various points through the receiver signal path to make sure that we have the correct bias voltage. If any of the op amps are failing generally, then you see a fail here. We have a bias voltage which hits one of the supply rails, or we have no signal making it through that particular op amp, so it will fail one of these tests. So the test results here actually give a fairly good indication of which op amp is broken, as well as confirm whether or not the entire board is working or not. So I'll now give a quick demonstration of testing one of the boards, and you'll hear on the audio as it goes through the various tests the audio tone changes, it gets louder and quieter. For people who actually have a QCX or a QCX Plus or QCX Mini, you will probably recognize some of these tones from what you hear during the alignment stages. And here's a close-up of the small OLED display so that you can see the results as they scroll up across the display. As I mentioned, the results are also logged to the serial terminal so that we can store a database of all the results and cross-reference those against a batch ID which is written on the label of the Qcx Mini, so if there are any future problems we'll be able to test that. So overall I was actually really pleased with how this Test Jig project turned out. Of course I'd be even more pleased if I didn't have to do something like this and spend the time on it, but it was quite a fun project to do, and we will be doing that for all future assembled boards with significant amount of SMD on them as well. I was actually really surprised that these 54 Pogo Pins can make reliable electrical contact between the two boards and not be off alignment or making some failed contact in some way, but they actually do work very reliably, so I was very pleasantly surprised by that. During the whole work of building it, I was of course fearing that at the end it wasn't going to work, so I was quite pleased when it did. Furthermore, of course, the fact that it survived testing 1,000 assembled boards was quite a shock as well. You know, you might think that things would get bent or misaligned or these Pogo pins would wear out somehow, but yep, they're really reliable, and 1,000 were tested without any issues with the Test Jig, so really happy with that. So in conclusion, the three problems were the voltage regulator, and that has been replaced by the 78M05 voltage regulator. The production issues with soldering with the board, that has been resolved by firing the factory that did the first batch and by appointing a different assembly house to do the second batch. We do a visual inspection too on all of the circuit boards, and we have not seen any repeat of components which were missing, cracked or poorly soldered, and there were no reports of any manual reworking being required in the second batch. The issue with operational amplifiers being defective has also been resolved by this Test Jig, which lets me do a comprehensive test of every aspect of the Qcx Mini's transmitter and receiver operation. With these combination of changes for the second batch, we can be approaching 100% sure that the board that we send to you, the customer, is operational without any defects. Thanks for watching. I hope you've enjoyed this video as much as I have enjoyed making it. Bye bye for now.